Sure.
Got your mic on.
Yeah.
Yeah. Okay.
Yep. And then the slides. Thanks.
Mr. Sujay is on travel, I think.
Oh, he is? Okay. Sujay, and there was who else? Did we used to have? Yeah, I know Jeff, and I know Jonathan. Was there a Kevin?
That's
Jeff.
Kevin.
No, I know Kevin, but there was another Kevin,
Do
right?
you have a control now?
Yes, I do. I thought there was. He's an aging guy. I'm good.
Not in our group.
Not in your group? Okay. Thought he
Maybe
was your
something
student.
Similar, but
Maybe.
okay.
Maybe. And there was another gentleman that stopped by. He was he's doing masters with you, and he was thinking of going to
Oh, yeah. Chris
Georgia Tech.
He is.
Chris. Okay. Okay.
No, you're thinking of, that's Chris Sane.
Okay.
Chris Sane is getting his master's and he's done.
Okay.
But the guy going to Georgia Tech
Or thinking about Georgia Tech at least.
didn't have good outcome of his qual.
Qual. Okay. Okay. All right.
And so he's going to go to Georgia Tech instead.
Sure. Sure.
He actually works for Al Valdez.
Oh, he's with Al. Okay.
Yeah.
Okay. All right.
What's his name? Caporipi?
I don't remember. He attended at 1 or 2 classes with us too. So yeah.
He was here too.
Okay. Okay. Well, it's a small crowd, but sometimes it's fun that way. Keep it a conversation. So, microgrids. We've talked a little bit about it, or a few times about it actually throughout the lecture series, but figured maybe we can talk about it today. Why microgrids? What are they? Talk a little bit about some of the utility scale microgrids that we have in the U.S. Talk about the Emeren Tech microgrid, and then go specifics in terms of, how would you consider the sizing of the different assets that you have for the microgrid. I thought it was interesting to talk about the step-up transformers that we've got tied to each one of these assets. Is it delta Y? Is it YY? And why we chose the different configurations for the different DERs. And then maybe take a look at the short circuit analysis that we did for the microgrid, and this will give a little bit more flavor to the discussion. But I assume you know microgrids and you have a good understanding of what they are. A lot of people think so. That's where the idea started. DOE has I think, an industry accepted definition that they put on the website, and that came out of the Microgrid Workshop report back in 2011. But it's really a group of just loads and DERs, or distributed energy resources, that are interconnected within an electrical boundary. And the idea that you can use these interconnected loads and DERs as a single controllable entity with respect to the grid that you can island or use in a grid-connected mode of operations. But that's the general definition. A lot of people think about it as small-scale power systems. So I got a chance to talk to folks at Bradley on Tuesday, engineers in Bradley University, and they want to talk about the changing grid and how it's looking like. And the high-level kind of concepts are now moving towards bringing all the larger power plants into smaller size, probably microgrids closer to the communities, closer to the neighborhoods, where you can provide a little bit more reliability, probably resilience. And there are a lot of efficiencies with bringing the power resources or the power generation resources closer to the communities in terms of reducing losses and whatnot. So that's, I think, where a lot of the industry is moving towards. And I'll be curious to know if there's research in that direction, or but that's kind of where it's headed, where we're seeing it head in the future. So small scale power plants or power systems is what folks are looking at in terms of power in terms of microgrids. Their ability to self-supply, of course, island, regulate, and distribute electricity to local customers is the high-level concept of what microgrids could one day do. Today, the concept's probably specifically around reliability and resiliency, but that's what the future probably is also looking at, is delivery of energy and supply of energy to customers.
You know about these things they have? You can buy them out at Farmer Fleet.
What are those?
Forget the brand name. You put them in your backyard, just like an air conditioner.
Uh-huh.
They connect to the natural gas.
Oh, really? No, I don't know about that.
Yeah, they're generators.
And generators. Wow.
Yeah,
Wow.
They just come on.
As backup, I assume, for failures, or you think these are folks that are running them more continuously.
No, they're for backup.
Backup. Yep. Yep.
But your power fails,
Sure.
Microgrid fails,
Sure.
there's an automatic transfer switch, which automatically transfers over to the
Natural gas.
natural gas.
Nice.
It's not instantaneous like yours,
Sure.
but it's probably a minute,
Sure. Sure.
get your power back on.
Yeah. Yeah. That's
And
very
you don't
cool.
do it, and you don't have to go to the gas station.
That's awesome. Yeah. Hooked up to the gas line. That's pretty cool.
Yeah.
I didn't know about that. I didn't know about that.
Yeah,
That's
they
pretty
were-
cool.
I forget the name of the brand, but you can buy them, and the beauty of it is they're quiet.
Sure.
You know, they're not like these gasoline
The loud ones. Yeah. Yeah.
generators, and you don't have to go to the gas station and fill them up with gas.
Right. Right. As long as you got gas, you've got them. That's very cool.
I was gonna buy one, and then I thought, when's the last time I needed one?
When was the last time you had a power outage? I had one last Friday.
Did you really?
Yeah.
Oh, that's right. I heard about that.
Were you out as well? The entire block was out.
No, I was
You
out.
were okay? Because I drove around a little bit, tried to help the crews figure out where the outage might be, and then they were working on Race Street, and it was a tree limb that fell down.
A bunch of them.
Yeah. But I didn't know if your house was out.
No,
Okay.
it's been, I think, about a year.
A year. Okay. Yeah, it's pretty interesting. We lost power for about 3 hours. So anyway, I was monitoring the entire time. The idea that Professor Sauer just shared, actually, we will see here at the TAC, where we use natural gas generation as a core component of the mixture of assets that we've got. So it's definitely used also at the utility scale level. So, when we talk about DERs and we think, again, reliability and resiliency would be number one use cases for them, but there are other needs that microgrids could provide. On top of reliability and resiliency, folks look for diversified energy sources. These could be for, again, environmental reasons, folks that are trying to hit environmental targets. Energy cost reduction, again, you could potentially be able to procure and purchase and produce energy at a cheaper level or cheaper probably cost than what it is out on the market, depending on what the market price would be. We're looking at some of these efficiencies in cost at the TAC. So we're doing economic dispatch with our assets at the TAC. Energy efficiency and demand response. These are also use cases that can be used or can be deployed as part of microgrids. Again, that feeds into both. Either if you're trying to do more energy efficiency for environmental purposes or for cost reduction, you can use it either way. And then the ability to provide ancillary services for the larger grid, whether that larger grid is the distribution system or the larger grid is really the transmission generation system. We think ancillary services are also transcending down to the distribution system probably in the future. So, yeah.
It's not obvious to me why microgrid has increased reliability and outage resiliency. I always thought it would be kind of the other way around. You have a smaller grid, it's more vulnerable to fluctuations.
That's a good thought. Today, the way microgrids work is they try to be in parallel with the larger grid all the time. And when you lose the larger grid, they're available for you to provide the added level of reliability or resiliency, whichever way you look at it, to the customer. So it started in behind the meter concept. So it didn't start as part of feeding the entire distribution system, but it started feeding houses or hospitals or campuses. That was a main idea when microgrids became known. 2004 when Sandy hit. Was it 2004? 2004, I think. 2005, 2004, around that time when Sandy hit. No, Sandy hit in 2014. Take that back. 2014, when Sandy hit, the campus of Cornell University and Princeton University were two of the campuses in the state of New York that had microgrids available to them on campus. So when regulators, investigators went back after the storm has hit and they looked at satellite images, they saw a dark area and two just lit up spots, which were Princeton and Cornell. And these locations had local resources, generation resources. They were able to provide energy back to their customers and reliability in that sense when the larger grid all died. And
In all fairness, Princeton is in New Jersey.
New Jersey, sure, agree. New Jersey and New York, right?
Yeah.
So they provided energy to critical facilities, hospitals, on staff, police and fire stations, critical infrastructure, critical applications, critical facilities came over. They sent students home, they sent professors home, they used their infrastructure to run some of the critical operations for the state. So that's where kind of a lot of the eyes started looking at microgrid because it was providing reliability to these specific loads. Now, how do you extend that concept to larger number of customers is where DOE started putting more funding and money in it. DOD started putting funding more for military applications, and utilities started taking that into consideration. So, hey, we should be able to provide that type of reliability and resiliency for some of the customers that would want that level of reliability and resiliency. Does that make sense?
Yeah.
So it's in that sense. It started behind the meter for specific loads and buildings, and then it grew towards, hey, let's do it for a circuit level or a substation level or a neighborhood level where you can provide energy to a larger number of customers, not just for one building or one house. So that's the reliability element of it. Now, the future, like I said, I was talking about the future. It's going towards maybe more and more microgrids that can connect and interconnect among each other and become a network of microgrids. So consider Champaign, for example. You could potentially have, say, 10 microgrids serving the city of Champaign. These are all interconnected. They're providing local energy to the customers. They're regulating and helping regulate the frequency and voltage among that local grid. And they're still tied to the larger grid, the transmission system and the subtransmission system that feeds and brings, additional energy or parallel energy to the city. They're still interconnected with it. If one microgrid goes down, some of the assets goes down, you could maybe distribute that load among the rest of the microgrids that are existing. So
It probably only works if you're being paid to be there, because you're not making money on your sales necessarily.
right,
You're getting a fee probably to be there in an emergency.
reserve or backup or be there, right?
Yeah.
Right.
Because otherwise, there's no business case.
True.
If somebody said, I'll pay you $2.50 for your gasoline, for your generator, money is just not going to do it.
Right.
They have to say, well, if you're there and you help us during hurricanes, we'll give you extra stuff.
Right. And which customers are wanting that level of reliability as well? So, for example, if you come to me, Tamer, and you say, hey, you're going to be out of power for a couple hours, or you pay premium, you pay an extra X amount of money to have that backup generation available to you all the time, that microgrid that sits somewhere that will provide you with energy all the time, no matter what, even if your power goes out from the main grid. Are you willing to pay that premium money? Some customers might be interested in that. Some might say, no, I can survive the 2-hour outage, it's okay. So the business case, again, depends on who's going to use it. Military applications can't and will not be okay with any type of outage. So resiliency and reliability for them is number one. They look at all kinds of contingencies, look at, I don't know what acronyms they use, but doomsday, and they look at DEFCON 1 and DEFCON 2 and these kind of concepts. That's what the military looks like. So they can't take any type of outage. Customers like you and I might be okay with a couple-hour outage, but not maybe a 6-hour outage or a full day outage. So it depends on what type of services these microgrids can provide would also evolve depending on what the customers are looking for. What Professor Sauer was talking about, hey, you get paid to be reserves, for example, or backup. You sit there, we'll pay you as a microgrid when you come on when there is a storm or when there is an emergency. That's again the ancillary service market that could exist for these type of assets. Make sense?
Yeah.
Good.
By the way,
Yeah.
I have a question about for other points I think make sense except the two. What's the point of diversification of energy sources? What's the benefits of that?
Yeah, some folks might have some environmental targets where they only want renewable type assets to be providing them with energy instead of other types of energy. So when you have a diversified set of DERs that are providing you, some are wind, some are some are solar,
But
some.
customer, I probably don't care about that. I just care about the reliability of the power quantity. But
You'll be surprised at what customers will want.
okay, so maybe
You'll be,
segment.
yeah. Some customers will say, I will pay again premium to get renewable only energy, and I don't want a blender of different types of resources that come my way. Right. Yeah. So it's just one of the goals that microgrids could provide to specific types of customers. Yeah. Sure. I figured also kind of mention some of the utility scale microgrids that exist out there in the U.S. This is Duke's microgrid. They also tout the microgrid as probably one of the more advanced microgrids in the U.S. And truly, they've put quite a bit of work in using it as a test bed and using it for research and whatnot. So Duke's microgrid consists of a battery and solar. Their battery is 500 kW H or kilowatt hours, 200 kVA, and it's 50 kW solar array. And they basically use that to feed a fire station. So one load that they use these assets to provide energy to. And they have three types of switches. They have normally closed. They call it the DG switch, and then they have an electronic switch, kind of like an interrupter or a Viper or a Diamondback. These are different type of switches on the market. I think it's a Viper that they have out there, which G&W makes. And then this is a manual disconnect switch, and then this is your utility side with the substation here feeding other customers. And they have a microgrid controller that basically is controlling all these assets and automating the operations of the microgrid to follow the load or to watch out for disturbances, to kind of disconnect from the utility accordingly. When do you run in parallel or in grid-connected mode? When do you run in islanded mode? They have a microgrid controller that does that. Take note that this. Go ahead. Take note that this is a centralized control, right? So it's one controller controlling all these assets. If you lose that microgrid controller, this microgrid does not go into function. So basically, you won't be able to automate the operations of the devices. These will depend on their own settings and protection settings and schemes that are in here. But there is no coordination and control among all these assets. Go ahead.
Yeah. So Tamer, for the microcontroller, this current microgrid controller has have a 3-level, the primary, secondary, tertiary, like traditional.
Not this one. This will have just secondary control.
AGC control.
Not sure if it has AGC control. I doubt it. AGC control looks at ancillary services. We'll need it's a MISO signal that comes in. I doubt this controller has it. This controller, like I said, is just for secondary control, meaning it's trying to look at the voltage at the bus, the frequency at the bus, and trying to regulate the voltage and the frequency of the bus for the inputs that are coming from these assets. So whatever the voltage here is, whatever from the battery and the solar, right? Whatever the kW, and the kVAR contribution coming in, it's trying to make sure that the voltage and the frequency are regulated here on the bus. And then it's also watching for disturbances. So anytime you lose the grid, it's going to do something, depending on what mode of operation it's currently in and where it wants to go.
Okay, is there any economical dispatch?
Not for Duke. They don't have that. Yeah. And they're not interested in that. I think their core use case is how do you integrate the assets? How do you do the actual reliability management of the microgrid? Yeah.
Another question: do you know how to determine the capacity of battery for a particular microgrid?
We'll talk about the one that we built in Champaign, so that will be coming up next. Yeah, sizing of the asset for it. Yeah. Here I don't know really what the load size for the fire station that they're trying to support here. This could be 10 kW, could be less. I'm not really sure. This could be oversized for what they have. But again, the battery could be there to last many hours. So I don't know what the exact use case that they had in here. And I didn't ask. I just looked at literature that they have produced and kind of just got that from their literature.
Where is this at?
It's McAlpin substation. So this is actually in Carolina, one of the Carolinas, North Carolina, I think, is where they have it. Yeah.
How long is that used?
This was built, I think, back in 2014 as well, and they use it all the time. I mean, I know the person that manages that facility, and you know, we speak frequently, and he does all kinds of tests and simulations, and he's very active in testing different modes of operation of the microgrid. Yeah, changing out transformers and doing simulations.
Testing freeze already put into the practical operation.
It's all practical operations, yes. Yes, research for practical operations, yeah, yeah. I think last thing he was looking at the impact of harmonics that are contributing to the grid. Another one that's out there that's utility scale is the San Diego Gas and Electric microgrid. This was part of a SPIDERS project, which was supported by DOE. And they have a ton of literature on it, but not very good graphics for what they actually built out at their facility. SDG&E uses this microgrid to provide energy to an isolated community in the area of Barago Springs, if you've ever visited California or if you know where that is. But it's like I said, isolated community. Folks that I actually went and visited the site, and these folks are folks from Hollywood, folks from top high-end businesses that they don't want anybody to know about them. So they want to kind of be off-grid. They're out by themselves, completely isolated. Like literally, you're in the middle of a valley between three mountains that they're just out in the boonies by themselves. Very isolated community. Long story short, there's one long sub-transmission feeder that feeds that community, and if that goes down, these folks could be out of power for days, not just hours. I mean days. It's just in forests and along mountains is where the supply line to them is. Last time they went out because of a fire, large forest fire around that area, and these guys were out for like 27 hours. And a lot of folks, there's a small clinic there that they need power. Backup generator sometimes does not last that long. So anyway, they use this project to support, or the idea for microgrid to support that community. The load of that community is about 4.6 megawatts. So San Diego Gas Electric went and fetched a couple of their large diesel generators. So they have two of them there on site that are 1.8 megawatts. And they went and bought batteries, each half a megawatt, and they put it also on site. And then right behind this facility here, there's a large solar field that's being built as well, that they were thinking of using that generation to help and augment what they've got in the assets here. But these were the assets when I visited that existed and they were using for the operations. All manual operations. So what would happen is if you lose that line, they'll send a troubleman to the substation, fire up the diesel gensets, right? And then go make sure that the batteries are basically push a button, turn the batteries into a voltage source, and then try to parallel those together. Once he's sure that these are both paralleled, this is all manual operation, he'll actually close the breaker for one. They have 3 feeders going out of that substation to feed that 4.6 megawatt load. So close one breaker for one feeder, keep some portion of the customers on for a few hours, then go around, open that breaker, close the second position on the second feeder, get another portion of the customer on for a couple hours, and then rotate those basically throughout the day until the main distribution line is back on. So very, very rudimentary, very, very manual operation. They tested it. It actually occurred during an outage that they had, and they were rotating the customers. So they will call the customers that are going to be on, say, hey, you're going to be on for 2 hours. So plan your day, put stuff in the fridge, I don't know, do what you need to do, sit in front of an air conditioner because, you're going to be out soon. And then they call the next batch of customers, say, hey, you're going to be coming on next. So very rudimentary, but that was, at the time, their microgrid. There were efforts, of course, to automate all this and put it all through their SCADA dispatch system, central dispatch system. But I don't know where it went after that.
There no control center or EMS?
There wasn't. There was basic SCADA, basically monitoring of the diesel and of the battery from their central location. But there was no control from remote central location, yeah. This one was a lot more advanced, and before we built the microgrid at Attack, this was considered the most advanced microgrid in the U.S., the Encore microgrid. So Encore is a utility in Texas, and that utility is also deregulated, so they can't own generation. One of the reasons they couldn't supply energy out to their customers is because, again, they can't own generation, so they weren't allowed to actually send any energy back to the grid. So all the energy that they had available to them at the microgrid, they used for their own loads and their own buildings. The type of generation they had a micro turbine, natural gas, 65 kW. They had a solar array on top of a carport, 100 kW. And they had a Tesla battery, 200 kW Tesla battery out there. But what was really unique there was the automation of it all. So again, centralized automation, centralized control, one big server that controlled all these assets and was able to match load, so basically do droop control when the natural gas genset will come on, become your voltage source, and operate the microgrid in islanded mode really, really well. They had some hardening and some cybersecurity assets in there because they were trying to use a tertiary control. So back to your very original question, what type of layers of control? This had primary, secondary, and tertiary in it. They were trying to do some economic optimization with when do you charge the battery with the solar versus the turbine, and when do you dispatch energy to your assets? Is it when energy out on the grid is cheaper, or when your assets locally available to you are cheaper? So I don't know if they were doing it right, but they had the capability, and they had started looking at that capability when we were visiting with them in 2015. You were scheduled to come with us on one of these trips, and he couldn't make it. We flew out of, I think there was a flight from Springfield directly to Dallas that we took and visited Encore. So pretty cool facility. They had a lot of trouble getting the battery to work. That was, again, a Tesla battery that they had. And just talking about the practical side of the business, it just was a black box to them. They couldn't really get its controller to talk to their central controller. They couldn't program it the way they wanted to program it. I think these were one of the very first generation Tesla batteries that were deployed as utility scale.
One of the walls?
No, that was not a wall one. Big one that was out on a pad mount installation. Should have changed the verbiage there. This is the Ameren microgrid. This is not Encore's microgrid. This is the Ameren microgrid that's here in Champaign. Have anybody here visited other than Professor Sauer? You have, Jonathan? Have you too? No?
Maybe I went there with Richard.
You should.
I will schedule time.
Yeah.
That'd be interesting.
Yeah.
But we see the wind turbine, right? So
Yep. So this one was, of course, different. We wanted it to be different. We wanted to be unique, kind of become the most advanced microgrid in the nation. So first thing we wanted to do with the microgrid is not serve behind the meter loads. We wanted to focus on serving the distribution feeder. So we want to make sure that we serve actual customers out of that microgrid. So when we installed it, our goal was to support this circuit here. This is circuit 371. It has about 200 customers on it. About 190 are residential, and the rest or 180 that are residential, and the rest are all commercial customers. So that was the main use case, is to provide reliability to these customers out on circuit 371. So we'll talk about how we sized the assets here and why we chose the different sizes of assets here. But what we got there was a 100 kW wind turbine. That's the wind turbine you're talking about there. 125 kW of solar. We have a battery that's a 1/4 megawatt, 250 kW battery. And then we have 2 natural gas gensets, each at 500 kW for a total of 1 megawatt. The differentiator here, other than we're feeding the real customers, all 200 customers, in an automated fashion, we're also using a decentralized control. So it's not one just controller like the rest of the microgrids that we saw. This is decentralized control. Yeah, I kept a slide that I shouldn't have. This should have been deleted.
What's the benefit of using this decentralized control?
Yeah. So remember, the centralized control we showed, for example, here at Duke. If this goes down, again, the microgrid does not operate anymore. You don't have overall control over all the assets. Coordinated control, I should say, of all the assets. So that's more of a reliability issue. Again, if you lose this one, you've lost control over your microgrid. A decentralized control that controls, that's got a controller at each of the assets. If one goes down, the rest of the assets can still operate within a microgrid environment. Does that make sense?
Yes. How about cost?
Sure. So yeah, that's an offset. Great question. So what are you going for? Are you going for reduced cost and average reliability? You could go with one central controller. You're going for, you're okay with high cost, but you want high reliability, then you should go with a decentralized control. I think the industry overall has mixed emotions on that, but the majority of folks, do believe in the redundancy and reliability that the decentralized provides.
Yeah, so my question is basically, cost a lot of money more than the centralized control?
Yes.
Which cost is come from the devices? Or hardware and software, probably depending on how that gets structured from a cost perspective. But yeah, instead of having just one brains for the entire microgrid, you're going to have multiple ones distributed among the assets. So sizing the microgrid. So again, depends on your objective. Our objective here was to support these 200 customers that we've got feeding through the substation. Here's what we did. First thing you do is you try to figure out what is your load requirement out there. So this is a 1-year load profile for that customer that we have. So the 200 customers, that's what their load profile look like. It peaks in the summer, so this is summer peaking circuit. Other circuits could be winter peaking, depending on what type of load you've got. We have a lot of winter peaking loads that use a lot of heaters during the winter. So electric loads that are mainly heated that causes a winter peak. Which costs more, summer peak and winter peak.
Costs more?
Sorry, I mean the load, total load is higher. Which one?
Oh yeah, the majority of our circuits are summer peaking circuits. Yeah. We see a lot of the winter peaking circuits actually on campuses. Again, these are a little bit older and have a lot more heating appliances that are using electricity. So. This circuit again is summer peaking. The peak for this circuit was 0.97 megawatts. So really, what we want to plan is to be able to support a 1 megawatt load. That's the number one goal at peak. Then we look at a few other scenarios of our circuit. So we looked and we tried to figure out, okay, what is the load distribution throughout the time? 90% of the time, this circuit load is about 0.75 megawatts, 3/4 of a megawatt. 50% of the time, the load is about half a megawatt or less. So again, when you start thinking about sizing your assets, what do you want to size for? Do you want to size for 100% reliability, which is it's going to cover the peak, or do you want to give 90% reliability, meaning 90% of the time when you have your load? What are you trying to size for? We decided we want to cover the spectrum, the entire spectrum for the entire year, no matter what, peak or not. So our assets have to support 1 megawatt at peak. But you can also consider the different times of the year. So if 90% of the time you're at 0.75 megawatts, maybe some of your assets can operate, in that sense where they're available 90% of the time, and you have maybe more of a backup type of topology for other assets that would provide that 1 megawatt support. So when we started design, we're looking at renewables plus storage, and we said, could that combination provide the load 90% of the time? And then for worst case scenario, right, when you don't have renewables, when you don't have storage, what is that asset that's going to provide that core reliability to the microgrid? Is it the natural gas in our case, right? It is important when you're looking at sizing your assets, not only at the load requirements, but also what physical requirements and regulatory requirements you might have. So physical requirements in terms of how much real estate do I have, right? Do I have enough area to put my solar panels on? Maybe be creative and use your roof of a house or a building. Use a roof of a carport, for example, if you have some of these assets. So you got to consider, as an engineer, all the options available to you or where to put some of these assets, right?